Today we're going to work on curve sketching, and I want to focus today on the rational equations. So we've done polynomials already, and today we're going to look at those rational equations or fractions. And we're going to do basically the same thing, just a little more, with finding the critical information that we've done before. So we have found our critical points, our increasing, decreasing intervals, our points of inflection. But now we're going to be looking at also our vertical asymptotes, our horizontal asymptotes, any slant asymptotes. And we're going to put that all together and be able to come up with a nice looking graph. So let's go ahead and look at an example to see what maybe we're going to see today. So here we have the graph, or the function f of x equals x squared plus 1 over x. So the first thing I'm going to do is go ahead and find my critical information. I'm going to have another sheet of paper here. So the first thing I'm going to do is find my first derivative. So that's going to tell me my increasing, decreasing intervals. So I have quotient rule. I have my low, d high, so x times 2x, minus my high, x squared plus 1, times derivative of the bottom, which is 1, divided by the denominator squared. Go ahead and clean that up. We have 2x squared minus x squared minus 1 divided by x squared. And that's going to give us x squared minus 1 over x squared. Now from there I can go ahead and find my critical values. I'm going to set my numerator equal to 0. That's going to tell me any horizontal tangent lines. And I'm also going to set x squared equal to 0, my denominator equal to 0. So that's going to be a critical value as well. If I go ahead and solve x squared minus 1 equals 0, I get x equals plus or minus 1. Solving x squared equals 0, I get x equals 0. So I'm going to go ahead and set up my intervals. And I have negative infinity. I always start at negative infinity, as I did with polynomials. I'm going to go to negative 1, my first critical value, negative 1 to my next critical value, which is 0, and then 0 to 1, which is my next critical value, and then 1 to infinity. So I always want to start with negative infinity and end at positive infinity, stopping at each of my critical values along the way. I'm going to test some values. Again, I want to test value in between this region, or in this region. So a test value may be negative 2, negative 1/2, 1/2, and 2. Now I can go ahead and look at the sign of f prime of x to see if it's increasing or decreasing. And again, we can look at some commonalities and some things that are going to happen with this function, this derivative. If I notice x squared minus 1, depending on what x squared is, this is going to depend on what the sign of this is. If it's less than 1, it's going to be negative. If it's more than 1, it's going to be positive. But our denominator, x squared, that's always going to be positive. So the numerator is going to determine what sign this function has. So if I create my signs, I already know that my denominator is always going to be positive. It doesn't matter what value I put in there. But if I put a negative 2 in, negative 2 squared, that's 4. 4 minus 1 gives me 3. That's a positive. So I have a positive divided by a positive, which gives me positive. But if I take my negative 1/2 and plug it in, negative 1/2 squared is 1/4. 1/4 is less than 1. 1/4 minus 1 gives me a negative value. Again, we're not interested in what the actual value is, but we know we have a negative. And a negative divided by a positive gives me a negative. If I plug in 1/2, again, same thing. 1/2 squared minus 1 is going to be a negative, and a negative divided by a positive is a negative. If I plug in 2, 2 squared is 4, minus 1 is 3. That's going to be a positive value. Positive divided by positive gives me a positive. So I'm going to see an increasing interval to a decrease, continuing to decrease there, and then another increase. So I see a change in my signs here, or my slopes. So I know that this point is going to be a relative value. And remember, if we used to go from increasing to a decrease, if I go from an increasing function to a decreasing function, that value is going to be a relative max. So we're going to find that point if I plug in negative 1 into the original function. So if I take negative 1, and I'm going to go ahead and square it, we're going to put it up here, f of negative 1. So I get 1 plus 1 divided by negative 1. That gives me 2 divided by negative 1, or negative 2. So I know I have a relative max at negative 1, negative 2. I can also go ahead and put in my 1 here. In this case, I'm going from a decreasing to an increasing. So if I go from decreasing or negative slopes to positive slopes or increasing, I know I'm going to have a relative minimum here. And again, I can go and plug in that 1 value, because that's going to be the value in between these two regions, or these two intervals. So if I find f of 1 gives me 1 squared, which is 1, plus 1 divided by 1, or 2. So if you want to go ahead and start plotting some points, you can. We have the point -1, -2, and we have the point 1, 2. Now we can go ahead and find our second derivative. Remembering our second derivative is going to tell us about our concavity and points of inflection. So I'm going to go ahead and take my simplified form of the first derivative there and find the second derivative. Again, I have a quotient rule. So I have low, which is x squared, derivative of the numerator, minus the numerator derivative of our denominator. And that's going to be divided by the denominator squared. I'm going to go ahead and clean that up, so I get 2x to the third. Multiply my 2x through here, I get a negative 2x to the third. Be careful, make sure you multiply your negative through as well. So we have a negative times a negative 1 is positive 1 times 2x gives us a positive 2x divided by x to the fourth. So cleaning that up, I end up with 2x divided by x to the fourth, which is going to reduce to 2 over x cubed. So I'm going to set my numerator, again, equal to 0, and I'm going to set my denominator equal to 0 to get my critical values, or my possible points of inflection, from my second derivative. 2 equals 0, that doesn't make sense to us, but x to the third, we get a value out. We get x equals 0. So we're going to go ahead and set up our intervals, again, negative infinity to our first point of interest, which is the x equals 0, and then 0 to our next point. Since we don't have any, it's going to be infinity. So those are my intervals. I'm going to go ahead and do my test values. My test value between negative infinity and 0, I can do -1, and 0 to infinity, I can plug in 1. Now I'm looking for the sign of the second derivative. Well, if I think about my second derivative, I had 2 over x to the third. 2 is always going to be positive, so the bottom x to the third, that's going to determine what our sign is. If x is negative, it's going to be negative. If x is positive, x to the third is going to be positive. So I plug in -1. Again, -1 to the third gives me a negative value. So that's going to be a negative sign. And if I plug in 1 to divide by a positive, that gives me a positive value. So I know I'm concave down from negative infinity to 0, but I'm concave up here between 0 and infinity. So I have a possible point of inflection here at 0. Again, remember, it's a possible point of inflection. We don't necessarily know, because what we got to do is take that 0 and plug it into our original equation to make sure that it is a point of inflection. So if I plug in 0, I get 0 squared plus 1, which is 1, divided by 0. Uh-oh, can't divide by 0, can we? So since we can't divide by 0, that is not a point of inflection, not a POI. So be careful with that, because what's actually happening there at 0? Well, we can go ahead then and talk about our next things, which is going to be our asymptotes. Notice how lengthy these problems become. So our asymptotes, we'll start with our vertical asymptotes and our holes. Well, holes to start with, I guess. Holes, we don't have any. X squared plus 1 doesn't factor for us. So we know we don't have any holes. No common factors between the numerator and denominator. But vertical asymptotes, I can have a vertical asymptote, set my denominator equal to 0, so I get x equals 0. So again, we can go ahead and draw that in if you wish. X equals 0 is going to be a vertical asymptote. So we have a nice dotted line there. Then we go to horizontal asymptotes. In our horizontal asymptotes, remember we're taking a limit as x goes to infinity of x squared plus 1 over x. And if I look at that, remember the extra stuff doesn't make sense to us, or isn't useful to us. So we take x squared divided by x, which gives us x. As x goes to infinity, that goes to infinity. So we know that that does not exist. Well, if we remember, we also have a slant asymptote, don't we? And a slant asymptote, remember, is going to occur when the degree of the denominator is exactly 1 less than the degree of the numerator. In this case, that does happen. So we can go ahead and divide that x into x squared plus 1. So x times what gives me x squared? Well, that's going to be x. So I get x squared. Bring down my 1. X doesn't go into 1. That is our remainder, so we can go ahead and get rid of that. So we have a slant asymptote at y equals x. So we can go ahead and draw in that line, y equals x. And there's my asymptote there. So now what we can do is go ahead and find anything else. Well, what about our zeros, our x-intercepts and our y-intercepts? So x-intercepts, remember x-intercepts? That's where we cross the x-axis, and it also means that y equals 0. So if we take y equal to 0 and set it equal to our function, x squared plus 1 over x, we can multiply the x over. 0 times x gives us 0. So we get 0 equals x squared plus 1. If I subtract 1 over, solving for x is going to equal the square root, plus or minus the square root of negative 1. Well, we know the square root of negative 1 is a complex number. We're only interested in the real number system, so we can get rid of that value as well. So we know we have no x-intercepts. So we go into our y-intercepts. And our y-intercepts are when x equals 0, so when we cross the y-axis. In that case, our x equals 0. So if we go ahead and plug in x equals 0, we get y equals 0 plus 1 over 0, which that can't happen either. So we know that that's not possible, so there's no y-intercept either. So let's go ahead and look and see what we have. Well, we know from negative infinity to negative 1, we're increasing. From negative 1 to 0, we're decreasing. And then 0 to 1, we're decreasing, then to an increasing. And we also have these asymptotes in here. So the only way we can get to these asymptotes and increasing is if it's going to be kind of in this form. And again, over here, we're going to start with these asymptotes. We're going to decrease. So the only way we can come into this point in decreasing is if we start high. Again, we start close to that asymptote. We're going to come down. And then coming out of it, we're going to start increasing. And we go out toward that asymptote. And that's going to also look at our concavity. Notice our concavity from negative infinity to 0, we're concave down. So we're opening down. And from 0 to infinity, we're concave up. So we're opening in the upward manner. And that gives us an example of sketching a graph that's rational. We can do another one. We'll do a quick one here, I suppose. And then we'll send you off on your way. So again, nothing new. Just to give you a little bit more work with it. So first thing I'm going to do is find my first derivative. First derivative here, I get x times 1 minus x plus 2 times 1 all over our denominator squared, which is x squared. Simplifying this, I get x minus 2 over x squared, which gives us negative 2 over x squared. Go ahead and set my numerator equal to 0 and denominator equal to 0. And I'll go through this on the quicker side on this time, just so you kind of see it. Negative 2 equals 0, that doesn't make sense. Here, x equals 0. So my intervals are going to be negative infinity to 0 and 0 to infinity. Again, x squared, if we think about things that are going to happen always with this function or this derivative, x squared is always going to be positive. Nope, I guess we need some test values before we do that. Negative 1 and 1. Now we look at the sign of f prime of x. So again, our denominator is always going to be positive. Doesn't matter what we plug in. Our numerator is negative 2. Negative 2 is always negative 2. It's not going to change. So we always get a negative over a negative. Or a negative and a negative there. So we negative divided by a positive, which is negative on both of them. So it's going to be decreasing on both of our intervals. That's going to be interesting, isn't it? All right. So what's happening at 0? If you think about 0, 0 is going to be a vertical asymptote. So if you want, we can go ahead and draw that in, even though we haven't defined it with our asymptotes. We know that that's going to happen, don't we? So we don't have a critical point. We don't have a max or a min at 0. It's just going to be an asymptote. So we can go ahead and do our second derivative. Our second derivative, taking our 2x to the second. To make your life easier, what I would suggest that we do is go ahead and bring that to the top as a negative exponent. So our derivative there is going to be 4x to the negative third, which we can clean that up as 4 over x to the third. Again, we're going to set our numerator equal to 0 and denominator equal to 0. The only value we get out is x equals 0 from our denominator, which that is going to play awfully close to what we did up in our first derivative test. So we can go ahead and test the same values, negative 1 and 1, but now we're looking at the sign of second derivative of x. Again, some commonalities. 4, that's always going to be a positive. And then x to the third. X to the third is going to take on the sign of our x value that we plug in. So if x is negative, it's going to be negative. If x is positive, it's going to be positive. So if I take negative 1 and plug it in, I do get that negative. 1 gives me a positive. So positive divided by a negative is a negative, and a positive divided by a positive is a positive. So I have concave down, and I have concave up. Do I have a point of inflection? Again, that value is going to happen when x equals 0 in between these two intervals. If I plug 0 into the original, remember, yes, that doesn't happen. We had an asymptote there, didn't we? So again, there is no POI for this problem, so no point of inflection. So let's go ahead and look at then our asymptotes. I think I can get it up here. So vertical asymptotes we've talked about, setting that denominator equal to 0, so x equals 0. Horizontal asymptotes, we're looking at the limit as x approaches 0 of x plus 1 over x. So as x goes to 0 of x plus 1 over x, again, that 1's not going to matter to us. We look at x over x, which gives us 1. So we have a horizontal asymptote here at 1. We're going to go ahead and look then at our y-intercepts and our x-intercepts. Something that should jump out to you, we don't have a y-intercept because we have an asymptote there. We can't cross over that vertical asymptote. So we can go ahead and look at our x-intercepts here. X-intercepts, we're going to set our y equal to 0. So y equals 0 equals x plus 2 over x. Multiply your x over. We get 0 equals x plus 2, or x equals a negative 2. So at negative 2, 0, we have a point. So do we have enough information to graph this? Well, we know that we are decreasing on the interval from negative infinity to 0. So we have this asymptote. We're going to get close, so we're going to start close to. We're going to come out. We have that point there that we can go through. And then we're going to continue to decrease to this asymptote. So we have enough information to get a rough sketch in. Again, we're not going to touch those asymptotes. We're going to get very close to them. We're concave down, just as our second derivative told us. Well, what's happening over in this area of our graph? We don't necessarily know at this point. So what we got to do then is to plug in another x value. It doesn't matter what x value we plug in because it's going to give us enough information to figure out what's happening with the graph. So I'm going to go ahead and say x equals 1. So I'm going to go ahead and find f of 1. Now we can go over here. So f of 1, I'm going to plug in 1. I get 1 plus 2 divided by 1. 1 plus 2 gives me 3, divided by 1 gives me 3. So I know I have the point 1, 3. Now, looking at the information I have from my charts, I know I'm decreasing from 0 to infinity, and I'm concave up from 0 to infinity. So if I decrease, that means I have to start high. I'm going to come down to my point, and then from that point I'm going to continue out, and I'm going to continue to go closer to that asymptote, that horizontal asymptote. So I'm going to decrease, I'm concave up, and I'm going to continue that curve up, but I'm going to get closer to this asymptote here. And that gives you the graph of what x plus 2 over x is going to look like. So that gives you a little idea of what we're going to look at, being able to graph rational expressions. Good luck. If you have questions, please let me know.